Okay. So, we have started pulse modulation, that is something we have already started, and we have told that we wish to actually establish the theory behind this pulse modulation. So, pulse modulation does take discrete samples of time, means signal, right. So, if we wish to do that, we have already proven the Nyquist theorem, that yes, there is a possibility that I can take just samples and that will still with a low pass filter, if we means put some criteria on the sampling, we have a possibility of getting the signal back, original signal back from those sampled signal. This is something we have already proven. Now, next what we wish to see, that yes, those samples which are means following the Nyquist criteria are actually the true representative of this signal. This is called the reconstruction theorem, okay, or the interpolation theorem. So, we will try to see that those samples are good enough, in certain way if we represent them, they actually represent the whole signal. Okay. So, let us try to see those things. So, what we have so far said, that this GT bar, right, which is the sampled version, what is that? That was actually at that instance we had some sample. Okay. So, that sample multiplied by delta at that point. Okay. So, let us call that sample at nth instance as GNTS. Okay. So, this just represents that at nth instant what is the sampled signal of that particular G. Okay. This should be multiplied by delta t minus NTS. Okay. So, at NTS what is the sample this one, and we are multiplying there with a delta. So, that must be this G bar, because G bar was nothing but that sampled with that strength there was a delta function at that location. So, that is what we are doing. So, this must be a representation, n goes from minus infinity to plus infinity, right. So, this is our G bar, right. Now, what we have said, that if it is following Nyquist criteria, if that is happening, then I can actually filter this. That is what we have said, that G bar t, if we try to see the frequency domain representation, that looks like this as long as Nyquist criteria is fulfilled. If I just put an ideal low pass filter which is having a band of B, okay, this must give me back my original signal. Okay. And also we need to see that this low pass filter that I will be putting, if I wish to go back to actual original G, what was the strength of this one? That was 1 by Ts. So, low pass filter must have a gain of Ts, so that they cancels each other. Okay. So, this has already gets means in terms of power gets reduced by 1 by Ts. If we can amplify them in terms of amplitude gets reduced by 1 by Ts. If we amplify them by Ts factor, this will originally go to our original GF. So, basically this pass through a low pass filter must give me GF as long as Nyquist criteria is fulfilled, right. So, what we have to do, this signal has to be passed through a ideal low pass filter of bandwidth B and gain Ts, right. So, this is a ideal low pass filter. So, at this side if we put G bar t, I must be getting GT. This is something we have understood as long as the sampling has been done with Nyquist criteria. Okay. That means that Ts is less than 1 by 2b. Okay. So, that condition has been already satisfied. Okay. So, what is my HF then? It is an ideal low pass filter which has a gain of Ts. So, it must have a gain and it is a box function. So, I can box function if we represent by pi. So, it must be a box function of let us say f frequency with a box width of 2b, because it should look like this from minus b to plus b. So, it is a box of width 2b. So, this is a box function with a gain Ts and this one, right. So, what is the corresponding HT? which is the impulse response of this filter. Okay. I know the HF corresponding HT, we know for a box function the corresponding Fourier HT will be Fourier inverse transform. So, that is a sinc function, we already know that. So, that sinc function should be Ts remains over here, that should be 2b because it is a 2b box function. So, 2b sinc sin c 2 pi bt, right. Now, let us say we have just satisfied the Nyquist criteria. Okay. That means our Ts, what had to happen? That must be less than 2b, right. Just satisfied means I also take the equality condition. There is a case that when I can take the equality condition, if the highest frequency, the signal we are considering, highest frequency of that is not an impulse. Okay, there is no impulse in the highest frequency and it almost goes to 0. Okay. If this criteria is fulfilled, then I can always sample it. So, what we are trying to say is like this: suppose I have a signal whose frequency response is this. What is this? This is a cos omega ct. If I now sample it, there is a problem. If I just do it with a Nyquist frequency of, means that sampling frequency is just matching with this, with the frequency of the sinusoidal. If that is the case, then I will have a problem, because this is a band limited signal of course, with a bandwidth of, suppose this is omega m, let us say. If this is omega m, the band, or if this is Fm, at Fm we have something. Okay. So, this is Fm. So, this is a band limited signal of highest frequency Fm, but at Fm it has a impulse. There if we start doing sampling, probably there will be superimposition of things. Okay. So, as long as there is no sample at the end of the band, we can always even do Nyquist sampling at that frequency. Okay. So, basically instead of writing this less than, I can also write less than equal to, and the best I can do is Ts equal to 1 by 2b. So, let us say we have done this sampling just with the Nyquist sampling rate. So, then Ts is equal to 1 by 2b. So, this becomes 1. So, I can write this as sinc 2 pi bt, right. So, this is all fine. Now, what I have to do is, I had a GT, right, which is represented as this summation. Let us say if I have k or n, whichever you put, k g k t s delta t minus k t s, you can even put n, earlier I was writing n. So, you can also do that. Okay. So, this is the GT and my HT is sinc 2 pi bt, right. So, what will be the output? It is convolution, we know it is a linear time invariant system because it is ideal this one. So, the output will be convolution of HT and g hat t. So, g hat t convolution of HT. What is that? This convoluted with this one convoluted with this one, but this is a delta function. So, convolution will just keep this signal intact, but it will just go at that delta location, right. So, what will happen? It will be just this g k t s delta t minus k t s, this whole thing convoluted with sinc 2 pi bt, right. Because this summation has nothing to do, no k factor over here. So, I can take this inside the summation. So, I can write k g k t s. So, this is just a delta convolution with this. So, delta t minus k t s convolution sinc 2 pi bt This is just a sinc function, but at that delta location. So, this must be sinc 2 pi b, instead of t it will be t minus k T s, right. So, what is that? This is actually summation k g k T s sinc 2 pi b t minus 2 pi b into k into T s. B into 2 b T s, we already know it is 1. So, this will remain as pi k, right. So, what exactly is happening? We already know that if we do Nyquist sampling, and from the frequency domain we have an understanding that if we put this filter, will be at the output will be just getting out the signal. So, this must be G t according to our understanding of the frequency domain. So, if this is G t, what is actually happening? Let us say this is my G t. I have now taken those samples at G k T s, right. And at that sample we are putting a sinc function, okay. So, at that position we are putting a sinc function with this parameter. So, basically that sinc, we will be putting a sinc which goes to 0 over here and then keeps on going, and here also there will be a sinc which goes to 0 over here, because this is actually just what is separation, that is 1 by 2 b, and this sinc function with 2 pi b t, this is just a shifting factor, it just takes it to next to this one, okay. So, basically they goes to at 1 by 2 b they goes to 0. So, it is just those sinc function, if you just put one after another, they will reconstruct the signal. So, basically what happens, we have understood now that a signal is nothing but you take those samples and put a sinc function over there, okay. So, that is all you will have to do. So, basically it is nothing but addition of all those sinc which recreates the signal. So, that is why it is called that this particular thing is the interpolation of the same signal. G t can be represented as an infinite sum like this one, infinite sum of sinc function. So, sinc becomes the basis, okay, almost like Fourier series. So, Fourier series we are saying that any signal can be, if it is a periodic signal, can be represented as the infinite sum of those exponential things. Here also it is an infinite sum of delayed sinc function having strength, where there also every frequency term was having strength. So, basically this sinc function becomes the basis function and having a strength which is exactly the sampled value at that location wherever that sinc is defined, okay. So, this is called the reconstruction theory of sampling. So, basically why we are able to do sampling? Because underlying we have this understanding, okay. We know that if I do sampling with Nyquist criteria, I can always, all those samples I can represent with a corresponding sinc function and I will be able to represent it. This passing through ideal low pass filter is nothing but that every sample is now getting that sinc function, because the filter has, ideal filter has impulse response of sinc. So, every pulse that comes and falls on that, at that location there will be a sinc function which will be getting created. So, basically this passing through ideal low pass filter just recreates those sinc function for every impulse that you give at the input, and that is what happens, because the summation of all those sinc functions are the reconstructed message signal. So, it gets reconstructed. So, reconstruction of a message signal is not a big deal, and that is why we know that sampling a signal will always give us opportunity to again reconstruct it later on, okay. So, this is something we should have in mind whenever we are doing it, but remember it can only be done if we are following Nyquist criteria, otherwise there will be distortion, okay. So, that particular distortion is called aliasing in the literature. So, basically whenever you have a band limited signal, okay, of let us say minus b to plus b, and when you are sampling, the sampling frequency is less than 2b. So, what will happen, the Fs might be, it will not be, this is 2b, it should be beyond that, but we do not suppose deliberately put it over here. So, what will happen, this will get repeated at every Fs. So, at this location there is a huge amount of aliasing which will be actually creating the signal like this, because they will be added. And then after that, even if you put a low pass filter, so what will happen, the signal will not be the original one, it will more look like this. This is the aliasing effect. So, basically whenever you do sampling, you have to be careful that you are employing Nyquist criteria, otherwise your sampling will not give you opportunity, even if you put an ideal low pass filter, will not give you opportunity to recreate your original message signal. So, that is very important. And that is why sampling theorem is there. Okay. So, now what we will try to do before even going towards the modulation, like amplitude modulation or pulse amplitude modulation or pulse position modulation, or the width modulation, what we will try to do, we will try to see some kind of sampling which are more practical. Okay. So, we will start discussing about some practical form of sampling. So, more practical sampling means, see, as you might have seen that I did sampling of a signal which is a band limited signal. So, once it is band limited, its power spectral density is something which is also band limited, and we integrate it from minus infinity to plus infinity, we get a finite power, right. But whenever we sample it, after sampling what is happening, within this 1 by Ts times its overall amplitude spectrum is getting reduced, but this is getting repeated up to infinity, right. So, overall power is becoming infinite. So, where from this, just by doing sampling we are getting infinite power, where from we are getting this power. So, basically what is happening, if you think about the sampler which was a train of delta function, we have already earlier proven that a delta function has, means single delta function has infinite energy. If that is the case, a delta function train will have infinite power, that is the source of power. So, basically you will never be able to achieve a delta function or a delta train or train of delta function. This is something which is not possible, because that is, if you wish to get that kind of signal, that will give you, means that will be actually generating infinite power, which is not possible. So, this ideal sampling which was proposed by Nyquist is not possible in practice. So, we have to now think about some sampling which are actually valid in practical scenario. So, what will happen, the pulses that we will be creating, that will be of finite width, it is not infinitesimally small like delta function. Delta function, the pulse width, we cannot talk about that width, that is infinitesimally small. We have already given one example in our earlier class, that we have said that is the pulse width, let us say make it minus epsilon by, means valid from minus epsilon by 2 to plus epsilon by 2, and the pulse width will be 1 by epsilon, then the area under it remains 1, and then we make epsilon tends to 0. So, what happens, this pulse width almost vanishes, because the pulse width is epsilon, that goes goes towards 0, and this goes to infinity. So, that is actually impulse. So, impulse, the pulse width is infinitesimally small, it tends to 0, whereas actual pulse will have a finite duration. So, now whatever modulation will be discussing, or whatever means sampling will be discussing with respect to a pulse of finite width or arbitrary shape pulse, which are practically generatable and available. Okay. So, therefore, suppose we multiply the signal GT with respect to that kind of pulse. Let us say we have a pulse Pt which looks like this. Okay, it goes to 0 very soon. So, this is our Pt, not an impulse. So, if this is the case, then when I do, suppose I take a train of this pulse, so how that will look like? So, there will be a pulse again after Ts, there will be another such pulse and so on, it will get repeated from minus infinity plus infinity. So, if my signal, original signal Gt, I start multiplying with this particular pulse, it will look like this, n or k whichever you put, kTs. Now, it will be multiplied not with delta, but this pulse. Right. So, this is what will be happening. But what we can say is any pulse is nothing but the convolution of that pulse with a delta. So, Pt minus Nts I can always write mathematically as this is nothing but Pt minus Nts convoluted with, or sorry, Pt convoluted with delta T minus Nts, right. So, whenever we do this convolution, this will be creating a pulse at similar shape pulse at T minus Nts. So, these two are equivalent representation, that is something we know from the theory of delta function. Because this Pt has nothing to do, it does not have sorry, this should be k, nothing to do with k. So, this Pt can go out with convolution. So, sum and convolution can be basically flipped. So, this happens to be gkTs into delta T minus kTs, right, and we term this as g tilde t. Okay. So, because this is not original sampling, so we are not writing it as g hat or g bar t, which was the original sampling with delta. So, this is sampled with that pulse, and then we could prove this. So, I can write that it is nothing but Pt, that pulse, this pulse convolution with, this is actually again we are going back to the sampling with delta train, okay, for mathematical representation. So, this we can write as g bar t. So, that is what happens whenever we actually sample it with any arbitrary pulse. So, we are actually theorizing it so that we can sample it with any arbitrary pulse, then we can take some finite width pulse probably. Okay. So, now if we just do Fourier transform of this, so basically if we write that as let us say capital G tilde f, that is the Fourier transform of G tilde t, let us say these are Fourier pair, and we also know Gt has a Fourier pair of Gf and Pt has a Fourier pair of Pf, suppose we know that. So, for the pulse also we know the Fourier transform. If that is the case, what will be G tilde t, G tilde f, because G tilde f we have already proven that is Pt convolution G hat or G bar t. So, it must be in frequency domain multiplication. So, that should be Pf, which is the Fourier transform of the pulse itself, multiplied by this G bar f, right. Now, this G bar f we have already evaluated earlier while doing the sampling theorem. So, we can write this Pf, this should be this, we have already proven that is 1 by Ts summation, if we just write n or k, let us write n. So, this is G, means f minus n Ts or Fs, right. So, this is something we have already proven, that this G hat t is this equal to this. This is something we have proven in our sampling theorem. by doing the Fourier series and then followed by a Fourier transform. So, this is what happens. So, basically what we get is 1 by Ts Pf, I can take Pf inside. So, if that is something you wish, so or otherwise I can keep Pf over here. So, basically it is summation n g f minus n fs, right. That is all that happens, right, whenever we have any arbitrary pulse. Now, for any arbitrary pulse we have a representation, right. So, if this pulse was ideally delta t, then what will be the corresponding Pf? That will be constant. So, if this is a constant, immediately what I get? I get my RDR representation, okay. And of course, that Ts gain has to be given, so that this Ts gets cancelled. So, basically if the pulse is something like this, I can always put a low pass filter with Ts gain, then Ts will be cancelled out with a frequency ideal low pass filter, and then because this Gf minus NFC just looks like this, it gets repeated, and then ideal low pass filtering will just give me back Gf. But now what is happening, this if I see this Gf minus Fc, that remains the same. Let us say we have just done the this Fs has been chosen, so that they are just equal to, this Fs is just equal to 2b. So, then this will be just repeated from there with a strength of each of them are 1 by Ts, right. So, this is my G, means this is actually my G hat or G bar F, right. This if I pass through a ideal low pass filter with a gain of Ts, so that Ts and 1 by Ts gets cancelled and I get this original Gf. But now because I have done the sampling with a pulse, this Pf should be multiplied with this function. Now, any non-ideal case of Pf, suppose let us say my Pf looks like this, or my Pt looks like this, a pulse of certain duration, or my Pt looks like this, okay. So, it is defined from minus Tp by 2 to plus Tp by 2, okay. Strength is 1. So, that is my Pt. Immediately what will become the Pf? Pf will look like a, because this is a box function, so it should be a sinc function. Because the width is Tp, this should be 1 by 2 Tp, okay. So, that should be my Pf. Now, this should be multiplied with this one. So, what will happen? Once I multiply, this particular Gf also will get a multiplication with this Pf. So, basically the Gf, whenever it gets multiplicated, the frequency spectrum of that Gf gets little bit distorted. So, this is what happens if I give a, instead of ideal pulse, if I give some other non-ideal pulse, I will always get a distortion. But this distortion I can restrict by what method? If I make this Tp smaller and smaller, what will happen? This 1 by 2 Tp will go away, further away, and this will almost become flatter in the region of interest from minus b to plus b. There it will not get any distortion due to that, due to the presence of the spectrum of Pf. So, that is what you will have to do whenever your pulse is not an impulse function. We can understand that, but what you can always do, that instead of having an impulse function, you can have a finite duration pulse, but lesser the width of the pulse, better you will be in terms of distortion of the original signal. And then if this is flat enough, so this will remain almost intact, I can now put a ideal low pass filtering and I can get my signal back without much distortion. So, this is the theorem when we do not put a impulse or let us say impulse function or a train of impulse for our sampling, because pulse will means pulse represented by impulse cannot be generated or recreated using any general or our day to day circuitry, because it requires infinite energy. So, if we give a finite duration pulse, The lesser the duration is, flatter its frequency response will be, and less amount of distortion you will be getting due to the presence of that pulse. Okay. So, in the next class what we will try to do, we will try to see different kind of pulse amplitude modulation by employing this practical pulse train. Okay. So, that is something we will try to study, and we will try to see what is the effect of them, and then probably we will have a brief discussion about what is pulse amplitude modulation, how we can employ pulse position modulation and pulse width modulation. Okay. Thank you.